Good morning. Welcome to this next lecture on complex variables. So if you recall, last time we had seen a theorem. We had seen theorem 1. We will not repeat the entire theorem, but main statements. It said that about a certain function which was continuous, if any one statement is true, the others are true. So one was that f had an antiderivative in D, okay. Then integrals of f between any 2 points z1 to z2 was path independent, and lastly integrals on closed contours was 0. Okay. So if any one statement is true, the other two are also true. Okay. And assuming statement 1 to be true, we saw the truth of the second, and assuming the second to be true, we saw the truth of the third, but 3 to 1 we did not see. I said it is complicated. Then one can see it in a proper complex variables class. Okay. Now to further explore this idea, let us look at, so let us take a look at an example to understand this theorem. So the example is this. I have a function 1 over z square. Okay. It is obvious that this function is not well behaved at the origin. Okay. At z equal to 0, this function is not well behaved. And let us consider a simple closed contour which is a circle of radius 1. The circle of radius 1. Okay. This is my C. Okay. Now the domain of this function, is obviously the entire complex plane minus the origin. Okay. Except the origin, the function is well defined all the way up to infinity. Okay. And it has an antiderivative. That means we have suddenly found that it has an antiderivative. That was the nature of the theorem. You suddenly find that any one of the statements is true about this function. So about this function there is an antiderivative. Okay. So what is that antiderivative? Which is minus 1 over z. This is the antiderivative. Why is that? Because d by dz of minus 1 over z happens to be equal to 1 over z square. Okay. In the same domain. Okay. And therefore the integral from z1 to z2 of dz over z square, okay, is equal to the antiderivative minus 1 by z evaluated between z1 and z2. Okay. And if it is a closed contour like we started off, the value is 0. If z1 happens to be equal to z2, then the integral is 0. Integral over this closed contour dz by z square equal to 0. Okay. Next, so we will see a contra example. Okay. The next example is a contra example. Okay. So there is this function 1 over z, okay, and again we will consider this closed contour C with a radius, okay, of 1, okay. For this function also, the domain is the entire complex plane except the origin. The function is ill behaved only at the origin, okay. Now supposedly it has an antiderivative which is log of z, okay. It has an antiderivative f of z equal to log of z such that f dash of z is equal to 1 over z, okay. But not, this antiderivative is not in the entire domain D, not in the entire domain D, okay. We will see why not in the entire domain D, okay. Now suppose we use this contour which we have, okay, and we start, since we are moving on a circle, okay, z can be represented as r e to the power of I theta, r is the radius, okay, which is a constant. So, n in this case 1, okay, in this case it is 1, then log of z is equal to log of r plus I theta, okay. So, we are examining the antiderivative, how it is behaving, we are looking at the behavior of the antiderivative, okay. So, log of, as we move on this, on the circle of radius r or radius 1, so log of z on this circle with radius r is log r plus I theta, okay, okay, and theta we start measuring from the real axis, we measure theta from the real axis, okay, and for us counterclockwise is positive always, okay, in complex variables counterclockwise is always positive. So now if I start at theta equal to 0, when theta is equal to 0, then my log of z is equal to log of r plus I0. I go full circle on this contour and I come back to the same point of z, okay. The z has come back to the same point when theta is 2 pi. What is z? Z is equal to r e to the power of I 2 pi, and hence r, it is back to the same point. Then what is log z? Log z now is equal to log of r plus I times twice pi. So the function log z has taken as jump, taken a jumps as we go from theta equal to 0 to theta equal to 2 pi, which as far as z is concerned is the same point, okay. So the function is discontinuous, log z now is discontinuous. If we consider the entire domain, in the entire domain, and therefore a valid a valid antiderivative does not exist. Does not exist. Over D. Okay. So, our f of z which is equal to 1 over z valid in this particular domain that excludes the origin does not have a valid antiderivative f of z. And therefore, what happens if I integrate now over this closed contour C dz over z, okay, and what is z? Z is, let us say, the unit circle e to the power I theta parameterized in terms of theta, then dz is equal to I e to the power I theta d theta, okay. Then this ends up as integral over theta going from 0 to 2 pi, okay. Dz is I e to the power I theta d theta by z is e to the power of I theta. So, this is integral 0 to 2 pi I d theta, which is equal to I into 2 I pi. Okay. So, an integral over a closed contour not equal to 0. Okay. Why? Because it does not have a valid antiderivative. Okay. So, we have explored theorem 1. Now, the next theorem is a very important theorem. Okay. It is called, so let us call it theorem 2. Theorem 2, which is the Cauchy Gorsat theorem. Cauchy Gorsat theorem. Okay. So, let me strictly go through the theorem and then we will see the implications. Okay. So, let us begin. Let C be a simple closed contour, SCC given parametrically as z equal to z of t, where a less than equal to t less than equal to b. Okay, t is a real variable extending between a and b. Next, let f of z be analytic. We should now know what analytic means. Okay. Analytic everywhere interior to and on C. So, there is this function, there is this simple closed contour, okay, in the complex plane C, okay, and this function f of z is analytic on and inside this closed contour. That means it has derivatives at every point. Okay. Then what? Then we have okay, integral on this closed contour f of z dz, okay, is equal to integral, okay, I will put this circle when we are doing a closed contour. So, this one should be familiar from your complex variables, okay, u of x comma y plus I of v x comma y, then dz is dx plus I dy, okay, that is now equal to, I will separate the real and imaginary parts. So, we have integral closed contour c u dx minus v dy plus I, okay, again integral over the closed contour c v dx plus u dy, okay. So, you can see that when I put this circle, it is a closed contour, integration on a closed contour, and I also put the direction which is counterclockwise, counterclockwise being considered the positive direction, okay. So, this familiarity I will assume you have from your earlier complex variables, okay. So, we have now reached a certain point, we have made a certain statement. Now, we need a certain certain result from calculus, okay, which is a Green's theorem, which says that if, so I will write a little below, if two real valued functions, if two real valued functions p x comma y and q x comma y together with their first order partial derivatives are continuous throughout a region R consisting of all points interior to and on C, okay. then integral, okay, p dx plus q dy, okay, is equal to integral r, this is c, okay. This is the line integral, this is the area integral, this is the line integral, this is the area integral, q partial derivative with respect to x minus p partial derivative with respect to y dx dy. Okay, this is the result. Okay, so you can see if you have p dx and q dy, it is q partial x minus p partial y. This is a very useful result. Okay, the line integral done in the counterclockwise direction. So this is a line integral going in the counterclockwise direction. Now how do we use this result for us? Okay, so we started out by saying that f of z is analytic, f of z is analytic for us, f of z is analytic for us, okay, which implies that it is continuous, okay, and it satisfies the CR conditions. Remember, these are necessary conditions or CR equations. Okay. Now for now we have only said f of z is analytic, but for now we assume, for now we assume that f dash of z is also continuous, f dash of z is also continuous. We do this because here p of x y, q of x y along with their first partial derivatives are continuous. So we are assuming that f dash here is continuous for the moment. Okay. That means since f of z is composed of uv, so what we have is u partial x, u partial y, v partial x and v partial y are continuous. Okay, that is the meaning. Now let us see, I have integral, okay, over the closed contour counterclockwise c f of z dz, okay, and we found out the full form earlier, which is integral u dx minus v dy, u dx minus v dy plus I times v dx plus u dy. Okay, it is right here. Okay. Now this part is a real integral, this part is a real integral, okay, and what is it? U is a function of x comma y, v is a function of x comma y, and their first partial derivatives are continuous. Same here, v is a function of x comma y, u is a function of x comma y, their first partial derivatives are continuous. So the Green's theorem now applies. So what happens to this? This ends up as an area integral over the region that C encloses, okay. But now you see what happens. We have Qx minus Py, okay. So this is minus Vx minus Uy dx dy plus I times the area that this closed contour encloses, okay. Now Ux minus Vy dx dy, okay. This for this part, this for this part, using this theorem. But f of z is analytic, and therefore it satisfies CR conditions, and therefore Ux is equal to Vy and Uy is equal to minus Vx, and therefore now you can see what happens here. Both these terms go to 0, so that is equal to 0, okay. That means my integral over the closed contour taken positively of f of z dz is equal to 0. So, very important theorem, okay. So, if a function is analytic on and inside a closed contour C, then the integral of the function along that closed contour is identically equal to 0, okay. So, this is a very powerful theorem. Now, here in here we additionally assumed, okay, we made an additional statement, assumed that f dash of z was continuous, okay. So, up till this was supposedly proved by Cauchy, okay, making spelling errors. But then Gorsat came along and removed this condition, removed the condition that f dash z had to be continuous, okay. So, now we truly have, if a function f of z, the function f of z is analytic on and inside a simple closed contour, then this integral over the closed contour of f of z dz is identically equal to 0. Okay. This is a very powerful theorem. So far it is a one-way theorem. That means f of z is analytic on and inside a closed contour, then this integral is 0. Okay. We have not said that if you find that this integral is 0, would it imply that f of z is analytic? No, we have not said that. So, it is a one-way theorem. Okay. So, again I leave you here. We will continue with these ideas in the next class. Thank you.